right, what I want you to start off with, just draw this picture. It doesn't have to be anything spectacular. Get a piece of scrap paper. You're going to hand this in. I'm going to collect it here in a few minutes. Also, we will go over some of the homework. I know some of the assignment might have been a little difficult, so we're going to go over quite a bit of it. So we want to try to rush things along. So right now, for about 2 or 3 or 4 minutes, start to draw this.
He wants to draw like the whole thing or just blank.
All right. What's your name? What we're going to cover today. And we're going to go back over the homework here in a second. So again, have your books open, ready to ask questions. But what we're going to cover today is dilations. That's the reason we drew this. For no other reason, give you something to do for a couple minutes. I'm looking at Jordan's picture here. We got this picture up here. Anytime you're taking a photograph of something, it's a dilation. All right? Or anytime you're making a drawing of something, if you're in art class, it's a dilation. 2 different kinds of dilations. What are they? Bigger and smaller, enlargement, reduction, increasing, decreasing. You could use any of those words. All those are just different ways to say the same thing about a dilation. Jordan's picture, is it a enlargement or a reduction?
Reduction.
It's a reduction of ours, right? So he made his smaller. Now, probably every one of you had to make it smaller because my screen up here is bigger than what you could fit on the paper. Even though Joseph somehow could.
I made it. I actually rotated it a little, so I lost some quality. Instead of like taking a picture from down here, I'm taking a picture from right here. That's not even.
But it didn't make it bigger, did it?
Dilation anymore.
All right, so that's what we're going to cover today. I'm not really going to do anything with these. I may hang a few of them up just to show off your artwork, but just get the idea that anytime you're taking a picture, you're dilating it, making it smaller or bigger, depending on what you're doing. All right, on the homework. You have your books out, follow along. I know some of this was difficult, so I want to make sure that I go back over it well for you. $478, right? Correct. Yeah. Questions? Problems you want to see worked off of 478? Make sure you ask. Don't be afraid to ask. Because I know some of this is difficult. That's why we're going over it. 32. Especially some of the ones that ask you to rotate about some crazy point and not at the origin and 50 degrees instead of 90. I know those are sort of difficult, especially because I told you not to, or you could have, but I didn't give you a protractor, a ruler, and all that stuff that you'd actually need to do it the correct way. Yeah, you said 32. Which capital letters in the alphabet produce the same letter after being rotated 180 degrees? Do I need to write out all the alphabet? Let's just go through it. Capital letters. A. Rotate 180 degrees. Is it the same? B. No, it's backwards, right? C. No, it's backwards. D. E. F. G. Sorry, I had to stop and think about my alphabet for a second. H.
Yeah.
So H is 1. This is problem 30. What problem is this? 32? So H is 1. I. I is 1. J. K. L,
Yeah, it's like on the
No,
hood.
it's on a computer. No.
capital letters, remember? L, what's L look like? There's only one way to write a capital L.
On the computer, a couple of those.
On a capital L on the
Yeah,
computer.
computer just puts on there.
Yeah.
Capital L, really?
Yeah. It looks like an I.
That should be a lowercase L, that shouldn't be a capital L.
That's always been like.
That's some stupid computer thing then. So we'll say no because that's not right. Try JKLM. No. What would M make? 180. Looks like a W. N. Does N?
Wait, yeah.
Let's try it and see. N's one that's sort of hard to think about. Capital N looks like that. What's it going to look like if I rotate it 180 degrees? Try to turn your head upside down and see it. Does it look the same?
Yep.
a little bit.
So N would work.
Hey, that hurt.
MNO. O works. P. Q. R. S.
Yes.
I got this.
S works. T.
No,
T work.
no.
It's upside down, right? If we do make a T,
Make a perpendicular sign.
perpendicular sign, very good. Damien couldn't think of it. STU, V, W, X,
Yes.
Y, about Z.
Yes.
Is that the one you were saying, Austin? You declared at the end and then we weren't that far yet, so. So how many of them is there?
5, 6, 7, 5, 6, 7.
7.
Seems like a little kid question. Yeah. It seems like something we just like.
Well, when you're doing rotations of symmetry and stuff,
I took too much time to find out.
you're doing, that didn't take that much time. You just had to go through your alphabet.
She knows her alphabet.
You coulda got out, you got little brothers or sisters,
Yeah.
so they probably got one of those printing old big line books that's got the alphabet right on the front. You coulda just looked at that and,
Remember those
Went
little
through real
girls?
quick.
They're in high school.
oh.
They don't have that stuff.
Other questions off the homework?
I know there's one, but I don't remember.
Is it?
Which one?
No.
I skipped it.
Which one did you say, Zach?
Oh, never mind, never mind.
Make sure you ask, because we haven't even done any of the hard ones yet.
How about pre-routine?
15. Problem 15. Draw the rotation image of each figure in a given direction about the center point and label the vertices. So this one they're just doing about the center point and rotating it 90 degrees clockwise. So have your notes out there so you can tell me what the rule is for 90 degrees clockwise. Take me a second. I'll graph this real quick.
You change them until you get to it.
Make sure you hang on to that until I get ready. So we got 0, 1. Oops, that's not 0, 1. Zero one's there. Everybody see that orange?
Yes.
Yeah, okay.
That's R. 5, 1. If I count wrong somewhere, please tell me. Why am I even doing this? What should I be doing?
Just swapping them and making the line negative.
So this is R, that's 0, 1. Here I yell at you guys all the time for starting off doing what?
Graph.
The graph. Don't start off doing the graph. Start off, let's come over here and let's write out the coordinates and then we'll change the coordinates and then we'll graph everything. I know your parents never do that, do they? Yell at you for doing something that they do? All this isn't about, I'm sorry, this isn't about the, 15 says, I was reading the wrong problem. 15 says about point -25 anyway, doesn't it? So do we have a rule for going negative, around the point -25? No. So, let me see here. Yeah, let's look that up there. This is S. This is T. I already start graphing them, so I'm gonna go ahead and finish. This is S. T is 2, 5. 4, 5. So that's our original shape. We want to rotate it about the point -2, -2, 5. That point right there. So we're rotating it about that point. We'll do red. Red shows up. I'm trying to use orange and brown, but I ain't really a brown on there.
You have to customize it for brown.
All right, so we want to go. Can you customize it that way?
Yeah.
Can,
Palette.
yeah. Oh, that's right. It gives that little honeycomb looking, beehive looking thing, doesn't it? Clockwise 90 degrees. So we want to go 90 degrees clockwise. So the shape, which way is the shape going to turn? You're going 90 degrees clockwise. Around that way. So it's going to go like around that way.
Yeah.
Now, again, what I said I wanted you to do on this, so this shape's actually gonna, it's like gonna turn, since we're on this point, it's over here, it's gonna turn, and it's gonna end up over in here somewhere,
I think I know how to do it.
alright? You could get out a protractor, a ruler, do all the stuff that would make it exact. What I want you to do for now is just connect, I'm gonna connect R to that center. Does everybody see how long that segment is? We want the new segment to be that same length, turning it this way, all right? So rotating this around this way. Well, we want our angle to be what here? 90 degrees. So we want that to be a right angle. Does that look like it's about the same length?
Yeah.
So this point right here is going to be what point? Start off R, what's it going to be? R prime. Turning it this way. S starts here. We connect S to our center point. Notice how long that is. We want it to be about the same length. The 90-degree angle right there.
What on earth are you doing?
Does that, watch, I'll show you. Does that look the same?
No, I don't know what you're doing.
So we put that there. What's the name going to be? Watch, I'll show you.
S prime.
S prime, good. Now we got T. T is right here. We want it to go around clockwise, 90 degrees, so we need to make, that looks like it's almost horizontal, all lines are straight or segments, but it's going to drop something like this. Does that look about the same length? Did I go too far? So somewhere about in there. About right. That's T prime. Now what do I do with all those? Connect them. Boy, mine looks terrible. Looks a lot bigger than it should. Probably, right? So you guys lied to me. This probably should have been back here somewhere, and this was back here a little bit. Told me they look the same length.
I said they did.
You said they didn't?
Yeah.
I didn't hear you. So all you're doing there, now I know it's sort of hard to see, this, can you sort of see that triangle when I fill it in there?
Oh, no, I can't say.
Must have did too much all at once on it. The orange one was our original triangle. When we turned it about this point, 90 degrees, that's where it ended up at. 90 degrees clockwise. And again, I know that's difficult to set and picture it. And what you should do is get out a protractor, measure each angle, 90 degrees, 90 degrees, 90 degrees, measure the length of each segment, the distance that original point is from the center point, and mark them off, which I didn't do, and you can tell because my triangles don't look the same. And it will come out exactly the same. But since I didn't want to send you home with a protractor and a ruler and make you do all that work, I just wanted you to do what I just did there and sort of eyeball it around. If they only wanted it to turn, instead of 90 degrees, they only wanted it to turn 60 degrees, then you just have to sort of figure out what a 60-degree angle is and move each one that way. 110 degrees, move it that way, so on and so on. The main thing is, Shelby, this making any sense? Main thing is, if I want to take a point, let's do this. Let's see here. Pointer options, let's erase all that. Let's say I want to take this point right here. That's my starting point, we'll call it point A. So I might be thinking of an angle for me, and I'll ask you for it here in a second. Ink color, let's change to, we'll do purple. So we got point A there, and we want to rotate that point about, I'm just going to make up a point right there. So we're going to rotate, probably shouldn't have made them so far apart. That point A, around this point, 180 degrees, 90 degrees, whatever we decide. All right? So what's the angle? 45 degrees. So we're going to rotate it 45 degrees. Do we want to go clockwise or counterclockwise? Counter. So counterclockwise. Doesn't make any difference. We're making something up here. Now all you're going to do, you're going to connect each corner of your shape. In this case, we only have one point. Connect each corner of your shape to that point. Then you are going to rotate it counterclockwise, which is going to be going around this way. So it's like you took a string and attached it to that point right there. And I got somebody else holding that. I'm holding one end of the string, you're holding the other end of the string, and you're rotating it around. That's all you're doing. All right? Now we said 45 degrees. So what we need to do when we connect this to this is know, all right, we're going in this direction, and we want to make what size of an angle right here?
45.
45 degrees. So a right angle is like this.
Maybe you should bisect it.
45 is like half that, right? If I could ever draw half of it. Somewhere in there, so it's about that much. So we'll say it's going to come down in here somewhere. It's going to fall on that dotted line there that I just made. How do we know where it's going to fall at on that dotted line?
Use a protractor.
Not a protractor this time, a ruler. We measure this length. Well, I have a ruler up here, but you might not have had a ruler. So I measure it. It's about that long. Come down here. It's going to be right about in that area. So we rotated that point 45 degrees with that as our center. All right. Now, if I wanted to, we got point A there. Let's go back and we'll put a point B up here. This would be A prime right here, right? put point B up there. If we want to rotate it 45 degrees counterclockwise, we do the exact same thing. We connect point B to that. We're going to rotate it this direction, 45 degrees. 45 degrees is going to be maybe somewhere like right through there. Again, if you had a protractor, could we tell exactly where it's going to be? Yeah. 45 degrees is going to fall in that segment right there, that dotted line that I just made. We want it to be the same length as it was originally, which is about, and do you really need a ruler? You could just use anything, right? You could use the edge of a piece of paper and just do what I'm doing there and say, all right, it's going to be that far out, so it's going to be somewhere about in there. We'll call that B prime. And let's say we have a point C. Other options in color. We have a point C up here somewhere. Now we've made a what? Triangle. We're going to draw. We're going to draw in this line connecting point C to that. We want it to go 45 degrees. Well, 45 degrees is going to be a little farther than B was, so somewhere like out in there. It's not going to look the same. If I measure it, probably I'm not out far enough yet. If I measure it, I'm about that far out. Yeah, I'm not anywhere near out far enough. Point C is going to be somewhere way out in here. Let's change our color again. Let's go with some other color. I connect all these. Does that triangle look like the red triangle? Yeah, it's just rotated down this way. If we took a piece of string and we had that triangle on the piece of string and rotate it down, that's what it'd look like. Okay? Don't make it harder than it is. Use those rules if they're doing 90 degrees, 180 degrees, 360 degrees. Use the rules. Make sure you do the coordinates and everything. If they ask you to do some crazy point, not the origin, or some crazy angle, 30, 60, anything else, then just decide here. If I put something like this on the test, am I going to throw a real big fit if your shape isn't exactly the same as the original? No. All right, because I'm asking you to just sort of get a picture of what it's going to look like, not be exact. Now, if it's 90 degrees about the origin, then do I want you to be exact? Yeah, because you have a rule for that, and you should be able to use that rule. Other questions on the page?
Oh, no.
Me and Chase will have trouble there.
Yeah, probably. You should just take them out on the paper stuff and all that.
Other questions? 4? Problem 4, I think that's the same kind of problem, isn't it? All right, problem 4, same kind of problem. I'm going to try to draw this up here as close as I possibly can. Probably won't be drawn very well. Alright, that's the picture they give us. This is problem 4. They want us to rotate that shape 60 degrees counterclockwise about point G. Which way is counterclockwise? Is this shape going to be turning this way or this way? Left. So it's going to be turning around this way, about that point. Again, it's like you took some string and attached it right there to the middle of that shape, and you just start rotating it around. Alright?
If you do all that lines and stuff that you did for the other thing, it's confusing to me.
Alright, so let me try it without drawing the lines and we'll see if we can figure it out. Alright, so we want to go 60 degrees. A 60-degree angle, if I'm looking at a 90-degree angle, a 60-degree angle should be about 2/3 of it, right? So maybe something like that. That's our 60-degree angle. So we want to turn this that much. I'm trying to think of a way I can do it without drawing all those lines.
The other's still in the ring.
Let's try it this way. If I connect, let's try it using my yardstick here. If I connect C to G, we want to turn it 60 degrees. If I could ever hold it still. So we got to decide when we're at 60 degrees. I don't know if I can decide that. You got a line right there. Let's do this. Connect this to this. I'm going to do this with this marker. We want to go 60 degrees. 60 degrees is about that angle. Does that look like about a 60-degree angle? Does that look about right? That's that long. So we want to come out here that far. Somewhere about in there. That's going to be C prime. So that's C prime right there. We're going to do the same thing with D. Connect it to G. We're rotating it 60 degrees this way. Does that look about 60 degrees?
Yeah.
So it's going to go up here somewhere. Should have measured as I was doing it. Our ruler's on the wrong end. About that far. So we go up here about that far. That's D prime. Now I know you said all these lines are confusing, right? But I'm going to erase them here in a minute. G to B. Connect G to B. Finger out of the way. It's about that long. We want to go 60 degrees. So we're going to go down this way. Maybe about there. B prime. I'm going to do this. Don't need that. B prime. C prime. D prime. What should happen when I connect all those?
Triangle?
Should it be a different triangle?
No.
Probably. Yeah, I wouldn't assume so.
Should be the same triangle, right? So let's connect them. That sort of look like the same triangle,
Yeah.
Looks like a piece of-
but what's happened to it?
I just look at it.
It's rotated around this way 60 degrees at that point. So if I connect this point right to the center of that triangle, you know, it's hard to decide where the center of a triangle is. You can't really make a center. It should rotate right over to here 60 degrees. Center there. And you don't have to connect to the center. You can could connect to any point on that triangle, and rotating it 60 degrees should put it in the same place regardless. So our triangles here, should use this. Triangles there, looks like this original triangle just moved around. Okay? That help any? Other questions? All right, today is the 26th. Is that right? Today is 26. Go ahead and start copying this down. We're going to cover dilations today. With dilations, what we're going to do with dilations, determine if a dilation is a enlargement or a reduction. How can you tell that? All right, if it gets bigger, it's an enlargement. If it gets smaller, it's a reduction. Now, part of what dilation is going to deal with, stuff that most of you probably don't care much for, when you start dealing with scale factors, a scale factor is normally given as a what? What kind of number? A fraction.
Or decimal.
A lot of people, not usually a decimal, it's usually a fraction, because it usually tells you this compares to this. All right? If I give you something as a decimal, does that tell you how they compare?
No.
It can be used sort of the same way, but it doesn't tell you how they compare. If you look at a model car, it says on the model car, probably says something like, probably says something like 1:5.
That's a huge model.
That's a ratio, right? Now, we probably, most of the time, are going to want it, instead of 1:5, we're going to want it written as a fraction, 1/5, or 5/1, depending on if it's an enlargement or a reduction. And that's a scale factor. Go ahead, I'll give you a minute to copy this down. All right, scale factor. How much bigger or smaller it gets? Remember, bigger is bigger is a enlargement. Smaller is a reduction. You might want to jot that in there somewhere. Enlargement, reduction. If you have an enlargement, what's absolute value mean again? Distance number is from 0 on the number line. So if, what this is saying here, if the absolute value of 1 is bigger, or I'm sorry, if the absolute value of your scale factor, that's R, that's your scale factor. If it's bigger than 1, then that means you're making your picture bigger. Right? So something like 5. Would that be an enlargement? Yeah, is it bigger than 1? Is the absolute value bigger than 1? How about -5? What's the absolute value of -5?
5.
5,
Still same.
still getting larger. So anything that's bigger than 1 on a number line, or farther away from 0 on the number line than 1, you're going to be making the shape bigger with that scale factor. If the reduction, all right, if it's a reduction, then your absolute value is going to be between 0 and 1. So usually, and I don't like to write this all the time because it doesn't always have to be this way, but usually if you're dealing with a scale factor and it's a reduction, your scale factor will be a fraction. 1/3, 4/5, 7/8, 1/2. So if you see a fraction about 99% of the time, then it's a reduction. Now, the reason I don't like to say that is because if I gave you a fraction like this, 5 compares to 2. That's an enlargement because is that bigger than 1? Yeah. So this would be an enlargement, not a reduction. But usually if it's a fraction, it'll be a reduction. If your scale factor happens to equal 1, sort of like turning something 360 degrees, these are the ones that you guys will like, because if your scale factor is 1, if I'm going to take a picture of this book and make a new drawing of it with a scale factor of 1, what's that new drawing going to look like? Exact same thing. So if they give you a shape and they say enlarge that, or they say use a scale factor of 1 and come up with the new shape, what are you going to draw? The exact same thing. So when this happens, this is called a congruency. Dilation. In other words, when you do the dilation, the new shape's exactly congruent to the other. Dilations are different than all the other transformations we've done before, because every other transformation we've done, rotations, reflections, and translations, when you got done, how did the original shape and the new shape compare? They were exactly the same. With dilations, they're not going to be exactly the same unless your scale factor is 1. All right, unless the scale factor is 1. If they give you a length, they say something like, so for this down here, they say segment AB is 32 units long. We'll say 32 meters long. And they want you to do some dilation on it, either make it bigger or smaller. I don't care. Give me a dilation number. You want to do a reduction or enlargement?
0.001.
Don't give me a decimal. Give me a 4. So if our R is 4, so are we enlarging this or reducing it?
We're gonna enlarge it.
Enlarge it. We're 4 times as much. All you do to come up with that new length for the new segment AB, A prime, B prime, is you just multiply the scale factor times the length of the original. So in this case, it'd just be 4 times 32. What's 2 times 4? 4 times 3? So what's the new length of A prime, B prime? 128 meters. So if you're wanting to change a length to the new length, you just multiply by the scale factor. I'll give you a minute to write this down. We're going to draw something with this, and Jalen, this time, yes, I will want you to draw what I draw with this. Different than what you've done in the past. In the past, if you had done dilations, they were on a coordinate system, and you drew them towards probably the center, the origin, something like that, just like with rotations. Right? This is going to be a little different. If we take, I'm going to try to draw it sort of small. We take a triangle, and will ever let me draw. We'll call it ABC. And we want to dilate that triangle towards this point. I'm going to change this real quick. I'm going to call it ABD. Because this is our center point, I'm going to call it C. Usually your center point will be called C. Why is that? C for center. Alright? It doesn't have to be, but we want to dilate that if the scale factor is greater than 0. So in other words, write this in right here. If R is positive. Never in the past probably have you dealt with negative scale factors, and that's where this is going to be a little different. So if your R, if your scale factor is positive, then this is what's going to happen. All right, ink color here. P prime. Yeah, I probably should have named my thing something different here. Let's change these letters because they use P and I forgot. P, Q. Yeah, we'll use D, it doesn't matter. P prime, so that's where P, this point P right here, that's where it's going to end up at, will lie on the ray. Does everybody remember that symbol means ray? The ray CP. Where would the ray CP go? Let's have somebody come up here and draw the ray CP. Remember? All right, Zach. Remember with CP, a ray, it has a starting point. So where's Zach going to put the pin originally? On C. And it's going to go out through what? P. And it's going to keep going, and he's going to put an arrow on the end. So it's that ray right there. If our R is greater than 0, if it's a positive number, whether it's a reduction or an enlargement, we don't know yet. But if it's bigger than 0, so positive, point P, or P prime, is going to fall somewhere on that ray. So P prime might be right here, could be right here, could be right here. Depends on what we're doing to it, what kind of enlargement or reduction we're doing to it. But it's going to fall on that right there somewhere. So P prime will fall somewhere in this area right through here.
There you go.
Now that doesn't make a whole lot of sense to you yet. It'll make more sense when we do this one down here. Yeah, it could, but
Is that the answer?
not usually.
That's the answer.
Well, no, that's just telling you that if this is positive, then this P prime is going to fall somewhere in here. Okay? So depending on what we did, you know, if our R was 2, then it's going to be an enlargement, and that's where
It'll be over there.
it's going to be over here. Okay? If it was a reduction, so in this area, reduction, getting smaller. This area over here, enlargement. I know that doesn't make a whole lot of sense right now, but it will here in a second when we do this one. So that's if P is, or I'm sorry, if your R is positive.
Freaking toes.
Your new point is going to fall on that ray somewhere. So D, if we were looking where D prime is going to fall, if I draw that through there, if I could have hit the point, we got a ray going through there. We know that D prime is going to fall somewhere on that ray. Not over here anywhere. It's going to be somewhere on that ray. Now, what's going to make this make more sense is when I come down here. If R is less than 0, so what's the scale factor this time? A negative. So if R is negative, if R is negative, then P prime is going to lie on CP prime, the ray CP prime. So in other words, let me draw another triangle here. Try to make it sort of look the same. Got P there, Q there, D there. C is out here somewhere. Now watch carefully on this one. This one's a little different. So instead of drawing our ray from C through P out this way to the left, where's it gonna start at? It's gonna go the other way. So it's gonna go like this. P's gonna come down through here,
And why?
and it's gonna be a ray down that way somewhere. So P prime is going to fall somewhere in that area.
It says CP, so should the middle one?
No, C P prime. P prime is gonna be out here, so it's gonna be out this way. Now, to explain that a little more, this ray that Zach drew for us a few minutes ago was ray CP. Well, this ray here, P prime, is the opposite ray of that. So it goes out in the opposite direction. Okay? So P prime is gonna fall somewhere in here. Yes, just.
What would happen if C were to be prime?
It wouldn't be, because C is your center point, and that's just the letter you give to that certain point. So if I do D, well, the ray CD would come out this way, but if we have a negative, we want the opposite ray, which would go out
Negative.
that way. So D prime would fall somewhere on that ray there. So D is going to end up here, D prime, sorry, is going to end up somewhere on that ray. If we did Q, boy, that's terrible. We did Q, and it was a negative R. Q prime is going to end up, whatever, draw straight, somewhere on that. So Q prime out here somewhere. Now, when you have a negative, let's look at this. P prime's on this one. Not that one. P prime is on this one. Let's get rid of that. P prime. D prime is up here. Q prime is here. Somewhere on those rays. What did it do to the shape?
We looked at.
It like flipped it over, didn't it? So when you do this, you're going to start off with a shape. Maybe that, let's say it starts like this, and this is A, B, C, D. When you have a negative scale factor, your new shape over here, what's this point going to be?
B.
B prime. It's going to like flip it over. All right? So when you have a negative scale factor, that's what it does. It sort of takes the shape, and it goes through all this, and it like flips it over. That's when you have a negative scale factor. Think.
Not ready?
Hit the wrong one.
No.
Think about it this way. We'll go to your eye here in a second. When you take a picture on a camera, and probably most of you don't have a clue now because you've never seen this kind of camera. When your folks used to take a picture on a camera, they had film inside the camera.
Film is dead.
And what's wrong? What was when you looked at the film? If you've ever seen a piece of film before, what was wrong with the image?
Oh, backwards.
It was backwards. It was backwards. All right. Let's do this. Let's hope each one of you looks in the mirror every now and then.
I do.
You looked in the mirror in the morning, so stand up, Damien. Damien looked in the mirror this morning. He had his shirt on. What was different about the picture of his shirt and the? Now, his reflection was a scale factor of 1 because the mirror didn't make it bigger or smaller, right? It's the same size. Yeah, if you have a funhouse mirror, then it'd be different. But his reflection would show that backwards, and that's what this does. When you have a negative scale factor, it like flips the image around. Okay? So it flips the image around. So just know that it sort of turns it over. Yes.
Could be B instead of B.
Yeah, I think you're right. It like flips it. You'll get it. There's an example in the book. If you look in your book, it's going to like flip it over and sort of turn it around.
Seriously, the only thing I got off the book with them examples. The I don't know what you did or anything.
Alright, so listen carefully, I'll get back over it real quick. If you have a positive scale factor, then your shape is either gonna end up here, in between the center point and the shape, if it's a reduction, or out here, if it's an enlargement. So it's like you got your shape here, and you got these rays coming off of it from wherever the center is. If you're in art class, you do point of perspective, right? If you're looking down the hallway, pick some point down there, and it all goes back to that, right? That's our center. That's our point of perspective. So this comes out here, and I can't draw straight. Comes out there. Those are like our lines from our point of perspective. If I could hit the points. When you're making something bigger, it's going to end up out here. When you're making something smaller, it's going to end up in here. If your scale factor, if your R is positive. Okay, so our shape might end up looking something like this. If I could draw it. Okay, but it's going to end up on those three rays right there. It might end up looking something like this. If we made it bigger. Okay? If I take that same shape and I draw those rays in again to this point C out here, the center, we still got our lines of perspective there. Mine are terrible, but trying to do it quickly. They come out here somewhere. If our R is negative, then your shape's going to end up out here, but it's going to be like flipped. All right? Think about this. Your eyeball. If you know anything about anatomy.
See everything upside down.
Exactly. That's what that's doing. Think of this as your eye. This is your eye. The shape's going through there. It's making it smaller, right? It's a reduction. It's going through there. Your eye has a negative scale factor because it turns everything upside down. It flips everything over. And that's what's going to happen here. All right, so this point right here is going to end up down here somewhere. This point is going to end up like here, and this point is going to end up on this one somewhere. Okay? And again, I think I said at the beginning, are you going to be confused by some of this?
I didn't know now.
Yeah. Everybody except for Shelby, because we know she's 1,000 times smarter than any of the rest of
No,
them.
after you.
If your eye did everything upside down, would it be like the entire room would be upside down? Like, would we be on like a ceiling?
If, and this is the easier stuff, if you are on a coordinate plane and your center is at the origin, then all you have to do is take each point, each corner, and use this rule. XY goes to R times X, comma, R times Y. R is what again? Scale factor. So you're going to take your scale factor. If the scale factor was 2, you just take 2 times each X, 2 times each Y. And it's going to give you new points, and you put those new points on there. Right? If your scale factor is 1/2, you take 1/2 times each X, 1/2 times each Y. And you graph those new points, and it's going to show your shape getting bigger or smaller. So if I made up some shape, let's make something easy so we can hurry through this. My pen over, start writing. I have that triangle. We need the coordinates. 2, 4, 6, so that's a -6, 3. This one is a -2, 3. And that one is 0, -2. And they tell us we're going about the origin, so we're reducing this down or enlarging it with the origin being our center, and we want a scale factor. Let's do a harder one. Let's do a reduction, because most of you don't like fractions. Give me a fraction. 1/2. So if we do 1/2, all you're going to do with each of these points, we'll call this point A, point B, point C, you're just going to take each of those ordered pairs and times each number by 1/2. So what's A prime going to end up in? What's 1/2 times -6? -3. What's 1/2 times a +3? 1.5 or 1.5. That's where A prime is going to be. About B prime. What's 1/2 times -2?
-1.
-1, good. What's 1/2 times 3? 1.5 again. Should be B prime. C prime. What's 1/2 times 0?
0. The second one will be negative.
What's 1/2 times -2?
-1.
-1. Now, if I graph all three of those, I'm going to change my ink color here so that I can show it. -3, 1.5, somewhere about there. That's A prime. -1, 1.5. -1, 1.5. That's B prime. 0, -1, 0, -1. That's C prime.
I think you're substantially smaller.
All right, so we used a reduction to get to this purple shape right here. Reduction was 1/2. That means for every 1 unit in the new shape, there was how many units in the old shape? 2. All right, so 1 to 2. What if I gave you a scale factor of 7 to 9? 7 units compared to 9 units. All right, what I need you to do, get out a sheet of paper. We got like 5 minutes. I'm going to do some of these for you. So keep your books open to this as you're writing it down. Get out a sheet of paper. Maybe I'll be nice tomorrow and do something special with it if everybody actually tries it. I don't know. Today when I looked around the room, it didn't look like a whole lot of people tried that last assignment and that